Abhishek. Abhishek, enter your reason number in the chat box.
Okay, sir.
Vishnuvardhan, enter your reason number in the chat box.
Done, sir.
Yes, thank you. So today I will complete this binary tree. So we will discuss about priority queue. So priority queue is nothing but it is a collection of zero or more elements. So each element has a priority or value. This operation can be performed on a priority queue. So like find an element like top operations, and if you want to insert a new element, it is similar to push operations, or remove or delete an element from the binary tree. Yeah, it is similar to pop operations. So using pop operations, you are able to eliminate the element. And if you want to insert the element into the binary tree, it is similar to your push operations what you have studied in stack. And find an element, if you want to find a particular node element, it is similar to top operation as you did in the stack operations you studied. So somebody joined the class. Shreyas, okay. Shreyas, enter your user number in the chat box.
Yes, sir.
So in a minimum priority queue is nothing but to which event you're giving a less priority. So that will be solved first. This can be used to find the operation, like it finds the element with minimum priority and remove the operations, removes the element. If you want to remove such element, so you can perform the remove operations. In a max priority queue, like if you are having a device for servicing, right? So when you provide a device for servicing to the customers, so you will allocate time for 1 hour, like say 1000 rupees, like but somebody should be there, but you will allocate the fixed time like 1 hour, right? But some customers they need more than 1 hour, like 1.5 hours, like 1.5 hours or 2 hours. Then they will provide extra amount for you. So then you can go for max priority queue. So this can be used to this can be used to find operation, like finds the element with max priority and removes the operations. Means if you want to remove that particular element, you can remove it. The elements in a priority queue need to have distinct priorities, like max priority or min priority, like that. Next, so linear list. The simplest way to represent a max priority queue is an unordered linear list. So there are two kinds of linear list is there. So ordered linear list and unordered linear list. Suppose that we have a priority queue with n elements. So the new elements are most easily inserted at the right end of this list using this equations. Location of I, which is equal to I. Suppose if you are inserting an element, means you need to perform the push operations. To perform the push operations, it takes big theta of one time. Suppose if you want to perform that pop operations, or suppose a pop operation requires a search for the element with largest priority followed by the removal of this element. So it takes big theta of n time to find out the largest element in an n element unordered list. and the removal time is also big theta of n. So searching to find the largest element in an unordered list, it takes big theta of n time. And if you want to perform the remove operations also, it takes big theta of n time. If a chain is used, push can be performed at the front of the chain. So in a big theta of one time, and it a pop operation, it takes a big theta of n time. If you are going to remove the element from the unordered list, then it takes time big theta of n. So alternate approach can be used in an ordered linear list. So you can arrange the element in increasing order, or you can arrange the element in decreasing order when we use an ordered chains. So pop time is, for each representation it takes big theta of 1, and push time for each representation is it takes big O of n time. So here we'll discuss about heaps. So here first we'll discuss about what is max tree and min tree. So a max or min tree is a tree in which the value in each node is greater than or equal to those in its children. So greater than in the max tree. So this is the parent element. So it has two children. So it will compare between left node element and right node element. The parent element, it will be compared with the left and right. First, what it will do, it will compare the left hand side elements and the right hand side element. In the left hand side element in the figure 1a, which is greater, 12 is greater compared to 10 and 8. In the right hand side element, 7 is greater than 6, right? Then it will compare this root element which is 14. It is compared with the left hand side element and right hand side element, left subtree element and right subtree element. So here the parent element which is greater than 12 and 7. So this is the max tree. So min tree is nothing but what happens here, the root element should be less compared to its children elements. So here the root element, it is 2. It will compare whether it is less than the left subtree element and the right subtree element. Yes, 2 is less than 7. Here what you will do, you will compare first the left side elements. So here in the left subtree, 7 is less than 10 and 8. Here 4 is less than 6. Then you need to compare this 7 with 2 and 4. So which one is less? So 2 is less when compared to 7 and 4. So you need to insert this 2 at the root, right? Again in the max tree figure 1b, here what you need to do is, this the parent element, you need to compare with this 6 and 5, right? This 6 is greater than 5 and 9 is greater than 6. So the maximum value is present at the root of the tree, root of the tree. Here in the figure 1c, this 30 is greater than 25. So 30, because of that in the max tree, 30 is present at the root of the tree. In the similar way, in the min trees in figure 2b, so 10 is less than 20 and 20 is less than 50. So here also 11, it is less than 21. So this is called min tree. So above examples are all binary trees. Why we call it as binary trees? Binary tree, it has only left subtree and right subtree. That's all. Not more than 2. Not more than 2. It has only 2 subtrees, one left subtree and one more is right subtree. That is why we call it as binary trees. It is not necessary for a max or min tree to be binary. So he's telling it is not required to be binary. it may be unordered binary tree also. So nodes of a max or min tree may have arbitrary number of children, or max or min trees may have arbitrary number of children, because it may not be, need not to be binary tree. So max or min heap. Then what is max or min heap? A max heap or min heap is a max or min tree that is also complete binary tree. So why we call max or min heap as a complete binary tree? Because so here in figure 1a you can see, so it has how many levels? It has 3 levels are present, right? So what complete binary tree concept tells that, so except the last level, other levels it should have complete elements. It should have complete elements. So understood. Other than the last level, except last level, other levels it should have complete tree elements. Right here, 14 it has two subtrees 12 and 7. So first level is complete, second level is complete, but the third level is incomplete. For 7, it is not having right subtree. Right subtree is absent. But even though it is absent, we call it as a complete binary tree, right? And here also, in this case, what happens? This is 9, but in the second level, so next element is absent. Right subtree element is absent, right? Then we cannot call this one as complete binary tree. This figure 1c is also not a complete binary tree. Here figure 2a, we can say it is a complete binary tree, because figure 2b is not complete binary tree, and figure 2c is not a complete binary tree. So here we'll see similar figure 2b, not min heap. So see here you can see in figure 1c, see this is first level, but last level need not to have this one. So this is the second level is not having yeah, any subtrees here. So here what he is telling is figure 2b not a min heap. He is telling figure 2b is not a min heap. Here also figure 1b is not a max heap. Figure 1b is not a max heap. So since a heap is a complete binary tree, a heap can be efficiently represented in one dimensional array. So you can represent the elements which are present in binary tree in terms of array representation. You can do it. So you need to store the elements from the top, and next left subtree element you need to store. Afterwards, right subtree elements. So in that way, from top level to the bottom level, you can represent the elements using an array. The position of the root is 1, that of its left child is 2, and the root child is at 3, and so on. So how the index position you will allocate is, here you can see the 20 is at position 1 in the array representation, and 15 left subtree element at array position 2, and right subtree element at array position 3. Next 14 at array position 4, and 10 at array position 5. Since a heap is a complete binary tree, a heap with 10 elements has height log base to n plus 1. A heap with 10 elements means, suppose it has 7 elements, means 7 plus 1, 8. So log base to 8, which is equal to 3. So the height of the binary tree, which is equal to 3, or levels of the binary tree, which is equal to 3. So here insertion into a max heap. So how do you insert an element into a max heap? So these are all examples, figure 3, A, B, C and D. Here in the max heap, what you are doing is you are inserting an element. Somebody has joined the class. Yes. So in this case, what you are doing is, suppose you are going to insert the element 5. Suppose if you are going to insert the element 5, but here 2 is less than 5, right? 2 is less than 5. You need to compare 5 with 2, because in the case of max heap, you need to arrange the elements according to its size. So because 5 is greater than 2, so 2 should be allocated at the left subtree of 5. You need to allocate. So here you can see figure 3a shows a max heap with 5 elements. It has 5 elements, 1, 2, 3, 4, 5. When an element is added to this heap, the resulting 6 element heap must have the structure shown in figure 3b. Suppose if you are inserting one element, if you have inserted one element, then the number of elements in the max heap, it becomes equal to 6. If the element to be inserted has value 1, the element, suppose other than 5, if you insert an element no 1, then no need to happify or change the structure of this tree, because 2 is greater than 1, right? So it satisfies the max tree, right? So no need to change the order, right? If the element to be inserted has value 1, it may be inserted as the left child of 2. You can insert it as left child of 2. So the figure 3b shows that structure. If the element to be inserted has value 5, the element cannot be inserted as the left child of 2, because 5 is greater than 2 will violate the max tree property. It will be violated if you do like that. Therefore, what we'll do, the 2 is moved down to its left child of figure 3c. So it has to be moved as a left child of figure 3c. So, and you need to bubble up this 5. So you can see here. Therefore, 2 is moved down to its left child in figure 3c, and 5 is bubbled up one node. Then we need to check for max heap, whether it satisfies the max tree property. Since the parent element 20 is at least as large as the element 5 being inserted, because 20 is greater than 5, no need to change the structure. Suppose that the element which one you are going to insert it, if it is 21, then the insertion strategies, it changes. So if you are inserting the element 21 in figure C, suppose if you are inserting a element 20, 21. So what it happens if you are inserting a 21 in figure A? So what happens? This 20 is greater than 2. So 2 has to take the left subtree of 20, 21. Then 21 and 15 need to be compared. So which one is greater? 21 is greater. Then you need to compare 21 with the parent element. Then if you compare the 21 with the parent element, which is having a 20, this 21 which is greater than 20. So 20 should be pushed down as a right subtree element, and 21 it should be bubbled up by one node as the root element of the tree. Next, suppose if you want to remove an element from a mag heap, so deletion from a mag heap. So here it depicts that three diagrams how to remove the element from the max tree. When an element is to be removed from a max heap, it is taken from the root of the heap. A removal from the max heap of figure 3D. You can see in figure 3D. Suppose if you are removing the element from figure 3D, result in the deletion of the element 21. So here what you are doing is, if you are going to remove the element 21, suppose if you are going to remove the element 21 from figure D, so it results in figure A, right? If you remove element 21, then it results in figure D, results in figure A, figure 3A. You need to happify. So since the resulting mag heap has only 5 elements, the binary tree of figure 3D needs to be rehappified. Next, to do this reapplication, remove the element in position 6, the element 2. So that is why I told. So figure 3D, so it converts into figure 3A if you remove the element 21. Now we have the right structure shown in figure 4A. 4A. So this one, right? Figure 4A. So here what we are doing now is, suppose from figure 3D, suppose if you eliminate 14 is there, 10 is there, 15. If you are removing the element 15 from figure 3D, right? Figure 3D or here, sorry, from figure 3A, suppose if you are removing the element 15, then we need to do the reapplication from the location 2, from the position 2, we will remove the element 15. Then we will compare 14 with 10. So which is greater? 14 is greater than 10. So 14 it will occupy the position, second position it will occupy. Then 10, so it will be written at, it will be written as the left subtree of this parent element. Left subtree of this parent element. So here no. So next we will discuss about the max heap initializations. So we have understood how to remove the element and how to do the reapplication in the max tree. In the case of min tree also, you can do the similar operation, you can do it. So next we will discuss about max heap initialization. So here you just write the position of each element. So 20 is present at position 1, next 12 is present at position 2, next 35 is present at position 3, next 15 is present at position 4, next 10 is present at position 5, 80 at 6, 30 at 7, and 17 at 8, and 2 at 9, and 10 1 at 10 position, right? So we will discuss how to perform the heap. Suppose we begin with an array of n element, say n is equal to 10. So it has, how many elements are present here? So total 10 elements are present. The priority of the element in A of 1 is to 10 is 20, 12, 35. So different elements which are present in this structure. 20 is present, 12, 35, 15, 10, 80, 30, 17, 2, and 1. So this complete binary tree is not a max heap. So this is not a max heap. Why it is not max heap? Because here 20 is less than 80 and 35 is less than 80. So this is not a max heap, right? So to happify, to make into max heap of figure 5a, now we need to convert it into max heap. So what we need to do? We begin with an last element that has a child 10. So last element is 10 that has a child 1, right? So this is the last element which has a child, which has a this last element which has a child 1 here. So this element is at position I is equal to n by 2 of the array. So this is at position I is equal to n by I is equal to n by 2. So n is equal to 10. So 10 by 2 it becomes equal to 5. So now I is at position 5. If the subtree that is rooted at this position is a max heap, then no work is done here. So here we'll check whether 10 is greater than 1. If 10 is greater than 1, then no need to do any work here. So it satisfies the max tree property. Next, if this subtree is not a max heap, then we need to adjust the subtree so that it is a heap. So following this adjustment, we examine the subtree whose root is at I minus 1, then I minus 2, and so on till you reach your root of the tree, right? So now we need to decrease the position one by one. So this is at position 5. So here I is equal to 5. Next I minus 1. I minus 1 means 5 minus 1, it becomes equal to 4. So here you need to compare, right? So which one is greater? 17 need to be compared with 2. Here 17 is greater than 2, and next 17 need to be compared with 15, right? So here 17 because 17 is greater than 15, so it doesn't satisfy the max tree property. It is not a max heap. So in order to make it, if you want to make it into max heap, so you have to do the hapification. So for doing that hapification, to convert it into a max heap, 17 and 15 need to be interchanged here, because 17 is greater than 15. 15 should be present at the left subtree of 17. So in figure 5b, we can see here the 17 and 15 in figure 1a, which is interchanged, right? Again, what you need to do? Again, you need to decrease the position by I minus 1 is war. Next I minus 2. If you perform I minus 2, so you will come here. I minus 2 means here you will come, right? At position 3. Here I is equal to 4. I is equal to 5. 5 minus 1 is 4. Next 5 minus 2 is 3. Is at position 3. So position 3 has a element 35, right? Next, what you need to do? You need to compare 80 with 30. You need to compare left subtree with right subtree element. Here 80 is greater than 30, right? Next, you need to compare this 80 with 35. Here 80 is greater than 35. So here you need to do the rehapification, because 80 is greater than 35. 35, it should come to the position 6, and 80 should be pushed or bubbled up by one node to the position 3. It should be pushed up to position 3. 80 and 35 need to be exchanged. So in figure 5C, you can see the 80 is interchanged with 35, right? Again, what you need to do, again the position, you need to decrease it, I minus 3. So 5 minus 3, it becomes equal to 2. Here you need to compare. 12 need to be compared with 17 and 10. Here 17 is greater than 12. First you need to compare the 17 with 10. Which is greater? 17 is greater. Next, what you need to do, 17 need to be compared with 12. It doesn't satisfy the max tree property. So to happify it, to make into max heap, you need to interchange 17 with 12, right? So 17 should be pushed up and 12 it should be pushed down, right? And this is shown in figure C. Here again, 12 is less than 15. So what you need to do? So 12 you should push it down, and 15 it should be pushed up, right? So this is done now. Next, again what you need to do? Again, after interchanging it, again you need to decrease the position by 1. So here I minus 1 is done, 2 is done, 3 is 1, 4 is 1, I minus 4 is done. Next I minus 5. So here I minus 5 will check, right? First we will need to check whether 7, we need to compare 17 with 80. Which one is greater? 80 is greater than 17. Next what you need to do, 80 need to be compared with 20, right? So which is greater? 80 is greater than 20. So what you need to do here, you need to do the rehappification. When you perform the rehappifications, right, 80 it will occupy the position 1 because it is greater than 20, and 20 should be pushed down. Then what you need to do here, because 20 is less than 35 and 30, so among 35 and 30, which is greater? 35 is greater, right, compared to 20, right? Compared to 30, 35 is greater. Then we need to compare this 35 with 20. 35 is greater than 20. So 20 it should be pushed down. It takes this position, and 35 it should be pushed up. So the rehappified max heap structure, it is shown in figure 5D. Figure 5D. So in the similar way, you can initialize the max heap. This is the max heap initialization. And min heap initializations, you do it for this tree diagram. You take this binary tree, so perform the min heap initialization. Do it. See, all of you do it, the min heap initialization.
Sir, question, sir.
This one, first one you take. 58. It has 10 elements, right? So this is the max heap initialization. I have told you how to replace it. So similar to that, min heap initialization, you do it. Take this diagram.
Okay, sir.
Do it. You take this diagram, write down this, and perform the min heap initialization. So in the maxi initializations, so we are concentrating on maximum element. In mini initialization, you need to consider the minimum element. Yes, to 6. So in the mini initialization also, you need to consider the last child node parent element. Last child node, this is the last child node parent element. From there you need to start and do the comparison, and you decrease the position by 1 and 1, so till you reach your root of the tree. So now if you explain me, after doing it, you just explain me, so how you are going to convert this into min heap.
Finally, each parent node should be having
Uh-huh.
compared to child node.
Yes. Hello.
So, like at the end, yes, sir.
So voice is breaking. Vishnuvardhan. Okay. What about others? Aditya. Aditya. Shreyas.
So doing.
Do it. Aditya? Aditya is not there. So in the chat box that Vishnu has entered the answer. So answer goes like that. You need allocated position 1, 1, 2, 10, 12, 15, 17, 20, 30, 35, 80. So this is the correct answer. So all of you can try this. You can draw the tree diagram and you can convert this unordered structured into either maxip or minheap. Maxip I explained, and that minheap, that answer it has been entered in the chat box. So you just draw the this binary tree diagram and do the comparisons one by one by decreasing its position and perform the swapping if it is required. If it is in the minheap, then no need to swap it. Otherwise, you need to swap it at each position after doing the comparison. And final a tree diagram you need to draw it. So all of you do this, okay? So tomorrow I will explain you the binary search tree. Okay, thank you. So thank you for attending this session.
Thank you, sir.
Thank you.